how many instances. So in case you have the 4 disk drive of this one, 2, 3, 4. Then when you create the assignment edges, it's also a good idea to start the arrow from one of the instance is clear. Okay? Each instance is assigned like this way. Okay? When you request the research, you don't know which instance is assigned, so it can be from process to circle to rectangle to the request. Any question? I think that's straightforward. I use actually the graph in my dissertation to get the PhD degree. At the time I used apply. It's quite similar idea. So I'm using region adjacent. Right. So from the images, when we have this kind of the images, this person, so I'd like to represent the relationship between or among the regions. So first I detect the region of face, region of the body, region of background. How many nodes? 1, 2, 3 nodes. And they are adjacent. Right there. They are adjacent. And they are adjacent. Then use the graph to represent the relationship in the graph. How can we use such a thing? To compare two images. Whether I can find a similar image from the database. This way we can save a lot of space, no matter what size of image, after we model this image into the graph. We need only 3 node information and 3 edge information. Drastically reduce. Also graph is good for what? Processing. We can get the benefit of graph theory, graph matching, graph card, graph something. The problem of such a graph theory is it's called the NP-hard. What does that mean, NP-hard? Any PhD student? No? What does that mean? I think that you know the NP-hard problem in your algorithm course as well as computation. I think the undergraduate we have such a course. I forgot the name of the course. Anyway, what does that mean, NP-hard problem? It's a
It can be solved in a finite time.
that means non-polynomial. Polynomial means it can be optimized using linear equation or the equation, it can be optimized. However, this graph theory is usually, not always, usually NP-hard, which means it's a brute force case. You need to check all the cases. When you have the 10, for example, I'd like to find this graph from bigger graph. Is there any index or any the efficient way? No, you need to check from the 1 node, 2 node, and you need to consider all cases. It's an NP-hard problem. NP-hard does not mean longer time. Okay? It doesn't mean the longer time or shorter time. It's a complexity. How complex your processing is. For example, binary search is log n. Okay? So log n big O notation. So 1 is the linear and n is an n square, but this one does not have, it's usually n square because when you have the n number of nodes. So you should be careful when you use such a graph theory to solve the problem. But it's still good for modeling complex data. So for example, using the resource allocation graph, this is the example. How many process we have? 3 process, P1 through P3. And how many resource? We have resource 1, resource 2, resource 3, and resource 4. And resource 1 has only one instance, for example CPU, and resource 2 we have two instances. Think about two networks. We have resource 3 we have the one memory, so something like that. So resource 4 has three instances. So this one means process 1 is holding. It's currently taking the resource 1 of instance in resource 2, but requesting the resource 1. At the same time, process 2 is holding resource 1 and also holding the resource 2, then requesting resource 3. And process 3 is holding resource 3. You see it? Deadlock situation 1. Deadlock 1.
Yes.
Deadlock.
Me too.
So first we can consider four characterization of the deadlock. All of them are mutual exclusion. In case you have the multiple, both of them are held by the process. Okay? So it's okay for the first one. Hold and wait. They are holding the resource and request the other. Third one. What was the third one? Non-preemptive. No process want to stop right away. And the circular way, you can see the circle over here. See deadlock 1. Looks like the deadlock, but actually not, because of this. Actually this does not request any other, right? So which means process 3 can be completed sometimes later. Eventually completed, terminated. Then resource 3 will be released, which means process 2 can acquire the resource 3. Then will be terminated when it is terminated. This one and the R1 will be released. Finally, process 1 can get the resource. So it is not the deadlock situation, even though you can find the circular wave, but because the process 3 is not holding and the request wait, because it doesn't request, does not wait any other. However, if process 3 is requesting R2, it may be deadlock situation. But I'm saying it may be. Okay? We will see why. Then what if process 3 requests the R2, then it is deadlock situation. We can find circular way. Okay? Two circular way, they are coupled. Circular way. What about this one? There are 4 processes and 2 resources with 2 instances for each, and P1 is waiting, R1 held by P3, P3 is requesting this one, and we can find circular way over here. Is it the deadlock situation? No, because the P4 and P2, eventually P2 and P4 will be completed, terminated, because they are not requesting other. Okay? However, if this one requests the other and the P2 is requesting the other, may cause the deadlock situation. So, if we can find the basic idea of the deadlock management is if we can find from the resource allocation graph, if we cannot find the circular way, definitely there's no deadlock. Okay? So it's okay. However, if we can find the circular way, it may be deadlock. Sometimes it may not be deadlock. Okay? Sometimes it may be deadlock, it may not be deadlock. So we will see the details of that to detect whether we can detect or whether we can solve the problem. Another problem of such a circular way, okay, like this one or this one. how much easy to find the circular wave in a graph. As I said, most, not always, but most of the such graph theory is NP-hard. NP-hard means it's not optimized solution. You don't know how long it takes. Okay? It depends on the number of process and number of resource. So for regarding to the computer research, you cannot guarantee when it can be solved. The problem, even to detect the deadlock, even to find the circular wave. Okay, that is the reason the operating system doesn't want to involve to deadlock situation if in case of deadlock, solve the application. Why you just can solve such a problem? So because of the NP-hard problem in graph theory. Then how can handle the deadlock situation? There are three different ways. One way is to prevent the deadlock or avoid the deadlock. Okay. Second solution is we can allow the system progress, okay, progress to the next state, okay, but if we can find the deadlock situation, then we solve that problem. How can we solve the problem? What we see? By allocating or the backup or we can find the solution. But the main difference between the first one and second one is, first one, do not progress, okay? Do not enter the next state if you can find any deadlock case. But the second is you allow the next state, which means you allocate the resource or the accept the request. Then if we can find the deadlock, we solve that problem. That is the detection, deadlock detection and recovery. The third solution is we ignore, like the most other operating system. How to first prevent? How to prevent the deadlock situation? What is the four main characteristics of the deadlock? Mutual exclusion, hold on wait, and non-preempt, and the circular wave. If you allow if you break one of these, one of four characterization, it may not cause the deadlock situation, right? Which means first, mutual exclusion. Why don't you allow that each resource can be shared by multiple resources? Then never happen deadlock situation. Okay, your resource always shared by many processes. However, if you allow such a thing, that may cause a lot of problem, right? Then why do we need any lock or the unlock or some synchronization problem? So not always you can use such a mutual exclusion. What about the hold and wait? Hold and wait, if you break hold and wait rule, which means the process cannot request, okay, if the process is holding another resource, which means it should be processed one by one. So I get the resource I read the data from hard disk drive, then complete it and release, then get the next one. The problem of this one is it will be slower and sometimes not possible to implement without holding the computer resource, okay? Then use another, no, that's not always possible. The third one is preemption, which means, so you can break the third rule, it's a non-preemptive. In other words, you can make the preemptive process, which means if somebody encounters such a problem, hold and wait, or the mutual exclusion, why don't you stop and cancel and restart? Okay, that is the preempt. However, the problem of such a thing is it takes longer time, right? So whenever you encounter such a hold and wait situation, stop and restart. And whenever you encounter such a situation and stop and start again, it takes a longer time. So not always is practical. Third one, Fourth one, you break the fourth one, which means no circular way. Which means, in other words, you need to make serializable process the progress. Have you ever heard about such a serializable thing or similar thing in the computer science?
Like first in, first out?
No, not always first come first serve. In database is very critical, such as serializable processing of what? Transaction. When you have multiple one, it has a lot of shared data, especially for shared buffer information data. Okay, the memory. How they can process multiple transactions? They need to consider serializable. In other words, in the one data space state to the another, moving to the another database state should be consistent. To preserve such a consistent, you need to find serializable processing of the multiple transactions. So it's the same thing. You need to find the serializable, the acquiring the resource lock, then the use, then release the usage. Serializable always. Okay. The problem of this one, in other words, if one process is holding this resource, then the other process, unless this is shareable, the other process should wait until this process is completed. Why? Because it's a serializable. Then once this process is completed, all the resource that is held by the process will be released. Until that time, the other process should wait. It's locked. Okay? So it's not practical. So deadlock prevention means you are going to break one of these. That makes sense. Then you may not enter, you definitely not enter deadlock situation. However, as we checked before, not always this solution can be applicable in real operating system. However, it can be. So deadlock prevention means, so we have the full characteristic of the deadlock situation. We break one of these, but not always is applicable in real operating system. So intra-exclusion, ordinary, no preemption, and circular way. So deadlock avoidance, so deadlock prevention, by breaking one of the characteristics, your entire system cannot have definitely cannot have the deadlock situation. Deadlock avoidance means using the current information. Using current information, you avoid, you get, you avoid such a deadlock situation. Okay, let's see. You need to check. So current state of your process and graph. Process resource can be represented by the contain process resource graph. So using this graph, if you can detect any deadlock situation, you are not going to allow it. Okay, avoid such a deadlock. That's the deadlock avoidance, which means the operating system does not enter deadlock situation. Okay, how can we do that? So using resource graph, we are going to find the safe state, whether this system is safe or not. Safe means no deadlock in resource allocation graph, which means you cannot find any circle in this graph. Okay? What if you can find such a circle? That means it's a deadlock situation, not always deadlock. As we have seen before, the circle does not mean always the deadlock, but it may be possible deadlock situation. So you are not going to enter such a state. Instead, reject, decline such a request. That may cause the deadlock. That's the deadlock avoidance, which means the system never enter deadlock situation. In the next solution, deadlock detection means you allow, okay, always allow any request, but at the same time, operating system check whether currently there exists deadlock or not. If you detect the deadlock, you did something. You need to do something to solve that problem. That is a deadlock detection. Deadlock detection allow the operating system enter the deadlock situation. Okay? Deadlock avoidance does not enter such a deadlock situation. That's the different thing. So how can we? Anyway, both of them need to check whether system is a safe state or not. So safe state means, so for example, so this is a simple example. So we have the three processes, okay? And let's think about the magnetic tape, which is not used currently, but there are systems that has many magnetic tapes for backup. So we have the 12 magnetic tapes. So process 0 maximum and most it need at least, not at least, maximum you need the 10 magnetic tape. Process 1 need 4. Process 2 need 9 total. If we have the 23 magnetic tape, there is no problem. However, we have how many? 12. Currently, how many are held by each process? 5 for P0, 2 for P1, 2 for P2, which means 9 of them are currently used by processes. Okay. Then how many remainder? 3 remainder. Then do you think that can be deadlock or not? If you can find order of process sequentially, then it is not enter deadlock, which means it's a safe state. Otherwise, it may cause the deadlock. First, can we complete the P0 first?
No.
No. We have only 3 available. So, what about the P1?
Yes.
P1 needs 2 more, right? What about the P2?
No.
No. P2 needs 7 more. So, first, P2 first. Then, P1 first. Once P1 is completed, how many available
5.
resources? It will return 4 of them even. So total 7 available. Right now 3 available. How many available? So P0 10 and need 5 more. P1 4 2 more. P2 9 2 more. Available 3. Okay? Then take the P1 first. P1 how many need? 2 more. Okay? How many available? 1. Then the current it has the 2 more. Okay? Total 6. Then it's completed. Return. Then how many available? 7 available. Then next, this one need 5 more. This one need 4 more. This one need 7 more. So we can execute this one. Why? We have enough available magnetic tape. So we can give the 4 of them to here. Currently, we need means we process need 5 more, 2 more, 2 more, right?
Yeah.
So I got confused. So again, so 5, 2, 2. So this is a 4, 9. Okay, and how many more need? It's a 5 more need, and this is the
2 more.
I currently had 5, and it's a 2 more. Currently 7, it's a 2 more, right? So then using available, first available is the 3. How many? I think the current need is 7, 2, 5. Current need. I think that doesn't make sense. Let's do it again. So let's say this is the maximum need. Okay, this is currently used by this process. Okay, this is currently used by this process. Then how many more need? So it's a 5 more need. This one is 2 more need. This one is a 7 more need. Okay, currently there are 3 available magnetic tape. Okay, then can we execute this one? No, because it needs 5. Can we execute this one 7? No. This one can be because it needs 2 more. So we can start P0, then borrow the 2 of the resource, then available is 1. Okay, then after P1 complete, all 4 will be returned. So currently 5 available. Right? 3 and 4. 3, 6. So it's a 7. 7 available total. Because it has a 3 and borrow 2 is gonna be total.
6.
Yes. No. It's a maximum 4. But it has 2, borrow 2. So currently 4 of them are heading. It's gonna be 5. 5. Yes. It's a 5. Thank you. Then this one is done. The next one is a 5 more, right? P0 can be completed. Okay? Then the P0 once it's completed, all 10 will be returned, right? So 10 available right now. Then it needs the 7 more, so P2 will be completed. So if we can find such a sequence of process without entering the deadlock situation, at that time we can say this current state is called safe state. Safe state means there will not be the deadlock situation, so you can allocate, you can enter the next step, next state. Okay? This will be used for Banker's algorithm to detect to avoid such a deadlock situation. Is the generalized solution of that. Okay, we consider how many available resource per process and how many maximum. Okay, how many are allocated per process, how many more resources are needed. Okay, it's a general version of this problem. That is the Banker's algorithm. So we will see the Banker's algorithm on Wednesday. Okay?
Thursday.
Thursday. Thank you. Okay. So this deadlock management is not part of the midterm exam. It will be minor, but it's important. So we will see on Thursday. Once again, the exam is on October 16th in the class hour. Or the distance learning students should take the exam on campus. Same time, only the online degree student can have the remote exam at the same time. Okay. Also, we do not have class on Tuesday. You can study for the midterm exam. For the midterm exam, 30% multiple choice and the other 70% open-ended question. Open-ended question is probably 5 to 6 questions. I'm not going to ask the coding itself, okay, but you should be able to understand the code. That code will be based on the basic structure of the program language, okay, to understand the algorithm, okay. Then the multiple choice, you will select one of the best answer regarding to the definition or the explanation of the some operating system topic. Okay, thank you and see you on Thursday.